Welcome back to the deep dive. For the last few sessions, we've really been down in the weeds, dissecting the theory. How do you model an attack mathematically? States, actions, MDPs.
All that foundational stuff.
Exactly. But today, we're finally making the jump. We're crossing that chasm from pure theory to, well, application. We're opening up Chapter 8, which is called Using and Extending These Models. And this feels pretty critical.
It really is. The groundwork's been laid, right?
Yeah.
So now the mission for you listening is to get how these powerful reinforcement learning simulations, these RL models we've talked about, how they actually plug into the bigger cybersecurity picture.
Right. We know they can find attack paths in simulations, but what does that mean?
Precisely. We're moving past just, academic pathfinding. We're asking that key question. So what? What does this mean for real-world threat intel, for actual defense? And we're going to walk through this chapter sequentially, topic by topic. We'll show you how these tools evolve from just being a planning aid to maybe becoming central to next-gen cyber defense.
Okay, sounds like a plan. Let's start right at the beginning of that application loop then. Section 8.1 is supplementing penetration testing. Now, first off, we have to acknowledge the human pen tester. They're not going anywhere.
Oh, absolutely not. That human element, the intuition, the context, understanding the legal and ethical lines, that's irreplaceable.
So if RL isn't replacing the human, how does it supplement what they do? Where's the value add?
It fundamentally changes the efficiency and the sheer depth of the planning phase. Think about how a pen test usually kicks off. You've got scoping, rules of engagement, legal approval.
All the necessary paperwork and setup.
Right. And within that, there's the recon and discovery part. That's 8.1.1, vulnerability discovery. And traditionally, that can be really manual, tedious work.
Just sifting through logs, looking at configs, trying to map out the attack surface.
Exactly. And it's prone to error just because of the massive volume of data in any modern network. Endpoints, logs, configs. It's overwhelming.
So the human tester is basically swimming in data, trying to figure out where to even poke first.
Precisely. And the core idea here is to shift that heavy lifting, that initial discovery, onto the RL model. These simulations, they run completely offline.
Okay, so before the human actually touches the live network.
Correct. The human sets the goal, the objective, like get to the domain controller, and the model then systematically churns out maybe hundreds, even thousands, of plausible high-reward attack paths. It basically sifts through, as the text says, mountains of previously ignored data.
And flags the key choke points.
Yeah, it identifies those critical paths or vulnerabilities that maximize the chance of success for the actual human-led assessment later. So the human brings the expertise and the context. The model provides the systematic, prioritized discovery. It speeds things up immensely.
Okay, that makes sense for speeding up discovery.
Yeah.
But you mentioned depth, and for me, the really big value seems to come in the next part, 8.1.2, path analysis. Because this moves us beyond just looking at, say, a single vulnerability score.
You're probably thinking of something like the CVSS score, right? The Common Vulnerability Scoring System.
Exactly. We all know it. And sometimes, let's be honest, we kind of despise it.
Well, yeah, and it's a perfect example of why this shift to path analysis is so needed. CVSS is, well, it's static. It gives a score based on the maximum potential impact of a vulnerability.
In a vacuum, almost.
Pretty much. It doesn't care where that vulnerability sits in the network, what defenses are around it, if an attacker can even reach it from the outside. It's totally agnostic to the actual network architecture, the attacker's real goal.
Right, so it tells you maybe how big the hole in the wall is, but not whether that hole leads to the broom closet or the master bedroom, so to speak.
That's a great analogy. And for defenders, they have finite time, finite budget. They simply can't patch every single vulnerability that pops up on a scan.
So they need to prioritize effectively.
Absolutely. Just knowing about individual vulnerabilities is like necessary groundwork, but it's completely insufficient for real defense. Path analysis gives you that crucial context, the cyber terrain, as the material calls it.
Okay, so walk me through that. Using your analogy, how does path analysis help decide which hole to patch?
Okay, so you find a vulnerability, maybe gets a CVSS score of 8.0 critical because it allows remote code execution. High score. But path analysis might show that this specific 8.0 vulnerability, it's on some isolated, non-critical web server. There are no clear lateral movement paths from there to the domain controller or the main financial database.
Okay.
Meanwhile, maybe there's another vulnerability, a simple configuration error, CVSS score 5.0 medium. But path analysis reveals that vulnerability exists on 5 different critical servers, and it provides a really easy, low-friction path straight to that master database.
Ah, so the prioritization flips completely. You'd focus on that medium severity flaw because it's part of a critical path.
Exactly. You prioritize based on common hosts or those shared vulnerabilities that are linchpins across multiple paths, leading to a high-value objective. It's about the chain, not just the individual links.
The RL models, they're simulating that entire chain.
Yes, the whole journey. The material breaks it down into roughly 8 phases, which should sound familiar to anyone in security. Reconnaissance, gathering IPs, domains. Then enumeration, finding active hosts, services, vulnerability analysis. Then exploitation, actually gaining access.
And then moving deeper in.
Right. Lateral movement, achieving persistence to maintain access, figuring out data exfiltration routes, and finally, covering tracks. The RL model learns the optimal sequence through that whole life cycle, but importantly, it's context aware. It knows the terrain.
Now, you mentioned context. We should probably touch on existing tools that do some form of path mapping. Bloodhound comes to mind, especially for Active Directory. How does that fit in?
Yeah, Bloodhound is a fantastic tool. It's really a brilliant application of graph theory, specifically for AD environments.
What does it actually map?
It takes all those Active Directory relationships, who can log in, where, what group memberships, grant what permissions, and it visualizes potential attacker routes. It's great at highlighting things like short paths from a regular user account straight to domain admin privileges.
So it's focused on the permissions and relationships within AD.
Primarily, yes, which is incredibly valuable. But the key distinction here, and where our RL models go further, is that they incorporate the entire cyber terrain, not just AD permissions. Meaning the RL models understand things like firewalls, not just as blocks, but as state transitions with associated difficulties or risks. They understand intrusion detection systems as points where the attacker might be observed. They can factor in the probability of success based on, say, operating system hardening levels or specific network controls being present.
Ah, so it's not just does the permission exist on paper, it's can the attacker realistically use it given the network's defenses?
Exactly. It's that deep contextualization and the ability to score the risk of an entire path, considering all these factors, that goes way beyond just looking at atomic vulnerabilities or permissions. That's really the power AI brings here.
Okay, that makes a lot of sense. Incorporating the actual network physics, the terrain, makes the output much more grounded in reality. But okay, if we have this realistic path, we still need to translate that insight into something actionable, something maybe executives or budget holders understand. Which brings us neatly to section 8.2, risk scoring.
Yeah, this is always a huge hurdle, isn't it? If we run these complex simulations but can't translate the results into clear, actionable metrics, especially ones tied to risk, we lose the buy-in we need to actually fix things.
And the current state, 8.2.1, is often a mess, right? Every security tool seems to have its own proprietary way of scoring risk.
It's very fragmented, makes comparisons really difficult, so we need some standardization. The material points towards established quantitative frameworks to bring some order to this.
Okay, what are the main ones discussed?
So 2 key methods are highlighted. First, there's AIR, that's factor analysis of information risk. This is a really systematic, repeatable methodology. Its main goal is to assess and manage information security risks by quantifying them specifically in financial terms.
Financial terms. Okay, that definitely speaks the language of business impact.
Yeah.
How does FAIR actually work? It sounds like it lines up well with what an RL model might output. Probabilities, potential losses.
It does. A FAIR breaks risk down into its core components. It really focuses on 2 main things. LEF, or loss event frequency, basically. How often is a successful attack likely to happen? And LM, loss magnitude. If an attack does succeed, what's the total financial cost?
Calculating potential financial loss.
Exactly. By quantifying these, organizations, particularly in sectors like finance, healthcare, critical infrastructure, where FAIR is quite common, they can start treating cyber risk more like other business risks. You're modeling a distribution of potential losses, not just slapping a subjective high, medium, or low label on it.
It forces a translation from technical flaws to business impact. That's a big shift. What's the second method mentioned?
The second one is probably more familiar visually to many people, the classic risk matrix. This is that grid, right?
Right.
You plot risks on 2 axes,
Yep.
likelihood, maybe ranging from rare to almost certain, and impact, from low to critical.
Yeah, the quadrant chart.
Right. And the goal is simply to visually pinpoint the risks that land in that top right quadrant, the high likelihood, high impact ones. Those are your immediate priorities for attention and, importantly, for budget allocation.
Okay, so we have FAIR for financial quantification and the risk matrix for visual prioritization. Now, let's connect this back to our RL models. Section 8.2.2 talks about the future state. How do the outputs from these RL simulations feed into and improve these risk scoring methods?
This is where the real value emerges, especially for that likelihood component in the risk matrix, or even feeding into the LEF calculation in FAIR.
How so? Because current likelihood often feels a bit generic,
Yeah.
like based on global stats.
Exactly. Current likelihood scores often rely on that kind of generic historical data. Globally, vulnerability type X is exploited in 20% of observed breaches, but that tells you almost nothing about the likelihood in your specific network.
Right, because your network isn't the global average network.
Precisely. It lacks context. It's a blunt instrument. Our RL models, though, they've been trained on the specific cyber terrain of the target network. They operate with sophisticated reward functions designed to mimic how a real adversary thinks, prioritizing ease, speed, stealth, value of the target. They provide actual prediction.
Prediction. So the model acts like a context-aware oracle for likelihood.
In a way, yes. The RL model predicts which vulnerabilities are actually likely to be exploited in this specific network, given its configuration and defenses, to achieve a valuable goal.
Could you give an example?
Sure, let's say there's that high CVSS vulnerability again. But the RL agent, when simulating attacks, consistently finds it easier or faster or stealthier to bypass it and use a different lower scoring vulnerability to reach the objective.
Because the path through the lower scoring one is better overall.
Right. In that context, the actual likelihood of the high CVSS vulnerability being exploited in that specific enterprise network drops significantly. The RL simulation provides much, much higher fidelity data for that likelihood component. It moves it from a generic guess to a context-aware prediction based on simulating an intelligent adversary's probable actions.
That's a really powerful shift from static analysis to genuinely predictive intelligence for risk. Okay, so we've used RL to enhance pen testing, path analysis, and risk scoring. Let's pivot now. Section 8.3 asks, where else can these models be applied? It looks like there are quite a few future synergies here, expanding the whole ecosystem.
Yeah, this is where we start moving beyond just aiding the human attacker or defender and into areas like automating defense, generating pure intelligence. It gets pretty broad.
Okay, let's take them one by one. First up, 8.3.1, simulation and threat detection. We know signature-based detection, like traditional antivirus, is always playing catch-up. How do RL simulations help break that cycle?
Well, the whole industry is moving towards behavioral detection, right? Looking for anomalous patterns, malicious activity, not just known file signatures. Because you need that to catch new zero-day attacks.
But the challenge is training those behavioral systems. You need good examples of bad behavior.
Exactly. You need realistic, anomalous attack behaviors, the tactics, techniques, and procedures, or TTPs, to train your detection systems effectively. And since real-world zero days and novel TTPs are, by definition, rare and often kept secret.
RL steps in to generate synthetic training data.
Precisely. The RL simulation becomes a TTP generator. It can create plausible, multi-step attack sequences that exhibit the kinds of behaviors, unusual lateral movement patterns, specific types of file access, weird network connections that match an attacker's goal, but maybe haven't been seen before in the wild.
So you train the detection system on the concept of the attack, not just its known signature.
That's a good way to put it. And while frameworks like Honor Air ATT and CK are fantastic for categorizing and understanding known TTPs, the RL simulation provides that foundational context, the network physics, the likely paths that an operator needs to actually apply ATT and CK operationally. The RL model generates the realistic examples of TTPs in action that ATT and CK then helps classify.
Okay, so generating training data for general threat detection. A more specific application mentioned is 8.3.2 ransomware detection. That seems like a good fit given how multi-stage ransomware has become.
Oh, definitely. Ransomware is almost a perfect example of a complex multi-stage RL problem. You've got that whole life cycle, the initial infection vector, the installation, setting up command and control, establishing persistence.
Then finding and encrypting the valuable data, or maybe exfiltrating it first for doxware.
Right. And just blocking one specific known ransomware executable isn't enough anymore. You need to detect the entire malicious progression.
So how does RL simulation help build a better ransomware detector?
Again, it's about simulating the full chain. You can train an RL agent with the specific goal of, say, maximizing the amount of critical data encrypted or exfiltrated within a simulated network.
It learns the most effective ransomware strategy for that network.
Exactly. The simulation then generates synthetic data, capturing that whole sequence of TTPs from getting the foothold, moving laterally, finding the data, maybe communicating with C2, and then executing the encryption payload. This synthetic data, mimicking a realistic ransomware operation on your specific kind of network, lets you build specialized detectors. These detectors are better equipped for high confidence detection, maybe even attribution, and potentially stopping the attack before the final encryption payload runs.
Okay, that makes sense. Moving on to 8.3.3, engineering new exploits. This sounds different. So far, we've talked about RL orchestrating known exploits, like using existing tools or modules. But the text says these models don't invent brand new zero days. Can RL help with that too?
Yeah, this is about pushing RL down a layer into the actual vulnerability discovery process itself. Engineering a new exploit, finding a zero day. That's often about creative experimentation, what security folks call tradecraft.
Finding subtle flaws in code or protocols.
Right. The idea here is that you can translate that craft, that process of experimentation, into another, more specialized RL problem.
How would that work? What's the state? What are the actions?
So instead of the state being the network map, the state space might become, say, the memory layout of a specific program you're targeting, or the configuration parameters of a web application's input fields. The actions would involve manipulating those inputs, think fuzzing, but guided by RL or trying to control the program's execution flow.
And the reward. What's the goal for the RL agent?
The reward function would be tied directly to achieving a desired outcome, like triggering a program crash in a specific way, overflowing a buffer, or successfully hijacking the program's control flow.
Ah, so it's automating the process of finding the magic sequence of inputs that break something.
Exactly. It's aiming to automate penetration testing at that much more granular atomic level, moving beyond just chaining known network vulnerabilities to actually finding new weaknesses within individual software packages or versions. It's like a dedicated RL agent focused purely on bug hunting.
That's pretty advanced stuff. Okay, let's shift gears slightly. 8.3.4 talks about extension to LLMs, large language models. We're seeing LLMs everywhere now. How do they fit into this RL-centric cyber framework? The text calls them a copilot.
Yeah, and copilot is a good term. LLMs are incredibly good at certain tasks that often drain a human analyst's time, particularly translation and summarization.
So automating the grunt work.
In part, yes. First, they can help draft reports. Imagine the RL simulation spits out a complex attack path with lots of technical steps. The LLM could potentially draft a comprehensive remediation plan or an executive summary based on that path.
Okay, report generation. That's useful.
Second, and maybe more importantly, they bridge the gap between technical jargon and business impact. The RL path might involve specific CVE numbers, exploit code snippets, buffer overflow details, really technical stuff. An LLM can translate that into plain language about the organizational risk. This attack path gives unauthorized access to the customer database, potentially leading to a data breach with an estimated cost of X.
That translation piece is huge for communicating upwards.
Definitely. And third, think about integration. If you connect an LLM to your SOAR platform security orchestration, automation, and response tools like XOR, for example, then the analyst could use natural language to query systems, correlate alerts from different tools, check on remediation status. The LLM becomes an intelligent interface to all that security data.
Right, speeding up the whole ODA loop. Observe, orient, decide, act for the human defender by handling the information retrieval and translation. Okay, next challenge.
Wow.
Knowing what's actually on your network. Section 8.3.5 is asset discovery and classification.
Yeah, this is a fundamental problem. Often, the attacker actually has limited information about what assets are truly valuable on a network they've just breached. They have to infer things.
Like that machine is running database software, so it probably holds important data.
Exactly. But here's the kicker. Often, the network owners also have an incomplete or inaccurate inventory of their own assets and what data resides where. It's a blind spot for both sides.
So how does the RL agent deal with this uncertainty? It needs to know where the valuable targets are to maximize its reward.
It does. So the RL agent can be programmed to take additional actions, maybe slightly riskier ones like deeper network scans or specific probing techniques, specifically to try and determine a host's role and the nature of the data or assets it holds.
But even scanning might not give a definitive answer, right?
True. Classification can still be ambiguous, and that's where the idea of model synergy comes in. You could have the RL agent doing the exploration, gathering clues about services running, security posture, maybe sniffing some data metadata. Then you use a separate supervised learning model trained specifically to classify assets. This classifier takes the clues gathered by the RL agent and assigns a classification, likely critical database, standard user workstation, etc.
So the RL agent explores and gathers evidence, and a classification model interprets that evidence?
Precisely. It's like the RL agent builds an internal threat intelligence database based on what an intelligent adversary would look for and prioritize, and the classifier labels it.
Okay, now for a really tough one. Section 8.3.6, attribution. The text calls this one of the holy grails of cybersecurity, figuring out who is behind an attack. It's notoriously hard.
It absolutely is. False flags, sophisticated obfuscation techniques. High-confidence attribution is rare. Traditionally, analysts try to piece it together by correlating everything, technical indicators like malware families, infrastructure overlaps, and especially TTP analysis. Frameworks like the Diamond Model or MITRE, ATT, and CK help structure this.
The core problem is getting reliable data, especially linking specific TTPs to specific actors, right? Because attackers try not to leave unique fingerprints.
Exactly. And labeled training data real-world attacks clearly tagged with "this was APT Group X" is incredibly scarce, especially data showing how APTX would operate on your specific network. Real attacks are messy and designed to be confusing.
So back to synthetic data. Is that the RL solution here too?
It's a genuinely revolutionary approach offered here, yes. Since we can't get enough good real data, we use RL to manufacture synthetic labeled data for attribution.
Okay, walk me through how that works. How do you generate data that looks like a specific APT?
Okay, step one, you design the RL agent's reward function, but instead of just rewarding get domain admin, you tailor the rewards to reflect the known preferences, biases, and common TTPs of a specific threat actor, let's say APTX. Maybe APTX strongly prefers using PowerShell for lateral movement and actively avoids noisy spanning techniques. You build those preferences into the reward structure.
Got it. So the RL agent is incentivized to behave like APTX would.
Exactly. It essentially becomes a simulated version of APTX operating within a simulation of your network environment. Then you run the simulation many times. This generates a whole set of plausible attack paths, clean, labeled synthetic data showing here's how APTX likely operates here.
Okay, so now you have tailored synthetic data for known actors. What's step two?
Step two involves using a specific type of machine learning model called a metric learning classifier. The text mentions one based on triplet loss.
Triplet loss. Sounds technical? What's the basic idea?
The core idea of triplet loss is learning by comparison. You feed the model three things at once. An anchor data point, say a segment of a synthetic attack path from our simulated APTX, a positive example, another different segment also from APTX, and a negative example, a segment from a different simulated actor, say APTY.
Okay, anchor, positive, negative. What does the model learn?
It learns to create a mathematical representation, an embedding space, where similar things are close together and dissimilar things are far apart. It's forced to push the anchor and the positive example closer together in this space, while pushing the anchor and the negative example further away. It learns to cluster based on behavioral similarity.
So it's essentially creating these unique behavioral fingerprints for each simulated APT group in this hidden mathematical space.
That's a perfect way to describe it. These latent space fingerprints capture the essence of their TTPs. Now, for step three, the payoff.
What happens when you detect a real attack?
When a segment of a real live attack path is detected on your network, you feed that segment into the trained classifier. The classifier embeds this real segment into that same latent space. Then it simply looks for the nearest neighbors. Which synthetic APT fingerprint is this real attack segment closest to?
And because the model learned the fingerprints from the synthetic data.
It allows for what's called zero-shot attribution. This is a really cool part. It means the system can potentially identify and attribute a novel attack campaign, one it has never explicitly seen in training, simply by matching its observed behavior to the closest synthesized APT profile it has seen. It gives you an attribution hypothesis with a quantifiable confidence score.
That ability to classify something entirely new, zero shot based on learned characteristics, is huge.
Yeah.
Okay, amazing potential there. Now let's flip the coin again. We need to think about defense. Section 8.3.7 is defensive modeling. Simulating attacks is great, but ultimately the goal is better defense.
Right. Up to this point, when we've talked about defense in the simulations, it's often been kind of simplified, maybe hard-coded reactions, like if alert X fires on the IDS, then the simulation assumes firewall rule Y blocks the attacker's IP.
A very static, predetermined response.
Exactly. The next logical step is to replace those simple, hard-coded defenses with actual AI-driven defensive models within the simulation.
An AI blue teen agent. What would that AI learn?
It would learn an optimal, real-time response policy. Faced with a simulated attack, it would learn to decide, what's the best countermeasure right now? Should I just block a port? Should I try to deceive the attacker? Should I isolate the compromised host completely? It needs to weigh the effectiveness against potential disruption.
And it would learn the timing, too. When to act.
Yes, balancing the speed of response against the confidence level that it's actually a real threat and not a false positive. And crucially, running these defense simulations allows you to extract recommendations for the human defenders in the real world.
Like what kind of recommendation?
Things like, based on simulating thousands of attacks against our AI defender, where is the optimal placement for our network sensors to maximize early detection? Which types of security tools or rule sets proved most effective at disrupting the most common or most dangerous simulated attack paths? It helps optimize the real defensive posture.
Okay, which inevitably leads us to the final point in this section, 8.3.8, AI versus AI. The source material seems pretty definitive that AI is going to play a bigger and bigger role on the offensive side, too.
It seems inevitable, automating attack discovery, crafting sophisticated spear phishing, using synthetic media, optimizing lateral movement. The offensive advantages are clear. It sets up an unavoidable AI arms race.
But the text also talks about a different kind of threat. AI attacks themselves, attacks targeting the AI systems. How are these different from standard cyber attacks?
They target the fundamental algorithms, the learning process of the AI, rather than just traditional software vulnerabilities. The text highlights two main types in this context.
Okay, what are they?
First, input attacks, sometimes called adversarial examples. Here, the attacker subtly manipulates the input data going into an AI system to make it produce the wrong output, even though the model itself is functioning correctly.
Can you give a cyber example?
Imagine an AI-based network intrusion detection system. An attacker might craft network traffic that looks benign to the AI, maybe by adding tiny, carefully calculated perturbations, so the AI ignores a genuinely malicious data flow. The AI model itself isn't broken, but its real-time judgment is tricked by the manipulated input. It effectively cloaks the attack.
Okay, tricking the model with bad input. What's the second type?
The second is poisoning attacks. These are more insidious because they target the training process itself. The attacker tries to corrupt the data used to train the AI model in the first place.
How'd that work?
You might subtly introduce malicious examples into the training dataset. For instance, if you're training an asset classification model like we discussed earlier, you might poison the data to teach the model that machines running database services are actually low-priority web servers.
So the model learns the wrong rules from the start.
Exactly. It builds a systemic blind spot or a flawed policy right into the AI's core logic because its education was corrupted.
Okay, these AI-specific attacks add another layer of complexity. Now, the source makes this really profound claim that cybersecurity is unique because it's AI's natural environment. Why cyber, specifically? Why not, say, self-driving cars or stock trading?
That's a really critical insight from the authors. Think about those other domains. An autonomous vehicle's AI is constantly interacting with and constrained by the real physical world, laws of physics, road conditions, unpredictable humans.
Physical constraints.
Algorithmic trading AI is constrained by market rules, economic principles, human psychology driving the market. But cybersecurity, it's almost purely informational. It's algorithms running on software and hardware, primarily interacting with other algorithms.
A battle fought entirely in the digital realm.
Yes. It's described as a perpetual high-stakes, naturalistic fight for survival and dominance between competing systems and algorithms. The speed, the complexity, the constant evolution, it happens at machine speed.
And the human response time is just too slow to keep up effectively.
That's the argument. Because the cyber conflict is so asymmetrical, attackers only need to find one way in, defenders need to block all ways, and because it evolves so rapidly, the human decision loop becomes a bottleneck. The authors strongly suggest that cyber might be the very first domain where humans are effectively forced to hand over primary control of the defense to a superior, comprehensive AI.
Because only an AI can integrate and correlate the sheer volume of data and react at the necessary speed.
Exactly. It requires that next level of intelligence, capable of seeing the whole picture and acting across immense, constantly shifting dimensions.
Wow. Okay, that definitely sets the stage for the final section, section 8.4, generalization. Because all this amazing simulation and AI capability is kind of pointless if you have to build and train a completely new custom RL model for every single network you encounter.
Precisely. That's the scalability wall. Section 8.4.1, Running Live, tackles this head-on. To make these models truly useful, a single trained RL agent needs to be effective on networks it's never seen before. It needs to generalize its knowledge.
And how do you train that kind of generalization? We can't just get access to thousands of different real-world networks to train on.
No, you can't. So you have to rely heavily on simulation and advanced machine learning techniques specifically designed for generalization. The text highlights a few key ones. First, domain randomization, or DR.
What's that goal?
During the simulation phase, you don't just train the agent on one static version of a network. You constantly vary the parameters, randomize the IP address schemes, change the number of hosts, swap out different firewall rule sets, vary the OS patch levels randomly.
So you're deliberately making the training environment unstable and diverse.
Exactly. It forces the agent to learn policies that are robust, policies that don't just work on one specific network configuration, but capture the underlying principles of how to navigate and attack networks in general.
Okay, domain randomization for robustness. What else?
Second, function approximation. We touched on this implicitly before. Network state spaces, all the possible combinations of vulnerabilities, logged-in users, system states are unimaginably huge. You can't possibly store a value for every state in a table.
Too big.
Way too big. So you absolutely must use things like deep neural networks as function approximators. They learn to map these massive, complex input states, what the network looks like, to good output actions, what the agent should do, in an efficient, compressed way.
Makes sense. What about adapting quickly to a new network when it first sees it?
That's where meta-learning comes in. This is often described as learning to learn. Instead of just training the model to learn one specific policy for one distribution of networks, you train it on a variety of learning tasks. The goal is for the model to learn a kind of foundational setting or a learning procedure that allows it to adapt very quickly with maybe just a few examples or interactions when it's dropped into a brand new, unseen network environment. It learns the skill of adaptation itself.
Learning how to learn fast. Okay. Any others?
And finally, ensemble methods. This is the idea of not relying on just one single RL agent. You might train multiple agents, perhaps each specialized in a different aspect of the attack lifecycle, one focused on initial access, one on lateral movement, one on data exfiltration. Then you combine their policies or predictions.
Like having a team of specialized AI agents.
Sort of. It helps mitigate the biases or weaknesses of any single agent and generally leads to more robust and better generalized performance overall.
It sounds like building a really sophisticated AI task force through simulation. Which brings us to the very last point in the chapter, 8.4.2, which feels quite philosophical. Teaching computers to attack computers.
Yeah, it steps back a bit here. It's acknowledging that what we're essentially doing by building these increasingly sophisticated attack and defense AIs is facilitating a form of true evolution within the cyber domain, a perpetual naturalistic struggle for survival and dominance fought between algorithms and systems.
And it draws a parallel to Alan Turing.
It does. It recalls Turing's idea that truly intelligent machines might not be explicitly programmed for every contingency, but rather raised like a child. They'd need to undergo a vast amount of experience, learn through interaction, analogous perhaps to the curriculum learning of domain randomization we just discussed, and potentially develop a form of intelligence very different from our own, one optimized for this purely digital conflict.
And the ultimate conclusion the material draws from this.
It's pretty compelling. Because cybersecurity is this unique domain, incredibly high stakes, intensely competitive, constantly changing at machine speed, it inherently demands that next level of intelligence. An intelligence capable of integrating and correlating information across almost infinite dimensions, something beyond current human capacity.
A holistic, AI-driven worldview for cyber.
Yes. And if we accept that this kind of superior AI is not just possible but likely necessary for future cyber defense, then the critical challenge shifts. It's no longer just about building the most effective AI. It becomes about how we ensure that the intelligence we create is designed ethically, responsibly, and actually reflects the values we want it to have as, in the text word, its inheritor.
That's a heavy thought to end on.
Yeah.
Okay, we have covered a massive amount of ground today, basically the entire application space discussed in Chapter 8. If you had to synthesize the key evolutions we talked about.
Well, we started with RL as a practical tool, enhancing penetration testing by providing that crucial context through path analysis, moving way beyond simple vulnerability scores. Then we saw how it could revolutionize risk scoring by providing truly predictive likelihood measures.
Right, making risk assessment far more accurate.
Then the simulation capability really took off, becoming this engine for generating vital synthetic data. Data to train better threat detectors, specialized ransomware detectors, and maybe most powerfully, enabling that zero-shot attribution of novel threat actors. And finally, we landed on the necessity of modeling defense with AI and confronting the reality of an AI versus AI arms race.
And I think the core aha moment here for you listening is really understanding that this isn't about AI replacing the human cyber expert, not at all. It's about equipping that expert with an incredibly powerful offline simulation capability. Think of it like a predictive digital twin of their network.
A twin that understands the complexities, the cyber terrain, and can forecast potential adversary behavior with a fidelity that static metrics like CVSS could never achieve.
That predictive power feels like the real game changer.
It absolutely is. That's the future of defense.
It really is. And the implication is that future cybersecurity won't just be about monitoring traffic logs or patching known vulnerabilities. It's going to be about predicting the entire attack strategy of potential adversaries synthesized by AI, before they even launch their first packet. Which leaves us with that final provocative thought for you to mull over. If the experts writing this material believe cyber will likely be the first domain where AI capability truly and decisively surpasses human capability, how do we, right now, ensure we design that intelligence not just to be ruthlessly effective, but also somehow benevolent?